Hi guys, I want to start by saying I'm really sorry if my mic quality is really bad because I broke my mic, so I can't use it. So which of the following quantities are the same for neutral atoms of two isotopes of the same element? Okay, so the thing about two isotopes of the same element is that they have the same number of protons, but they have a different number of neutrons. Okay, like let's say you have two isotopes over here. The bottom is going to be the atomic number, and let's say it's 45, and here it's going to be 45. And the number of neutrons is going to be, let's say, like 100. So that means for the second isotope, because the number of neutrons are never the same, it's going to be 101. So if these two are the atomic number and they're the same, so this is correct, and that also means there's the same number of electrons and protons. Which of the following are the results obtained in Rutherford's experiment? Okay, so what is Rutherford's experiment? It's basically a very general idea is that it's a nucleus surrounded by electrons. Okay, so this one is basically memorizing. So it's most of the atom is empty space, and most of the mass, the atom is concentrated in a small heavy nucleus, and the nucleus of an atom is positively charged. Why is the nucleus positively charged? Because it's made of protons and neutrons, hence making it positively charged. You also might think electrons of an atom are negatively charged. Why isn't that correct? Well, that's not what they're asking for. The electrons of an atom are negatively charged. While that statement may be correct, it's not a result of Rutherford's experiment. Guys, this is the same question as the last one, okay? Okay, so in order for a nuclide, whatever, to be of the same element, the atomic number has to be the same. It doesn't matter what the mass number is. So if we see for 10, there's no other option that also has 10 in it. So that's why it can't be correct, because we need 2, which the atomic number is the same. And it's the same thing with 30 and the same thing with 32. But the atomic number for these two options are the same, because again, we don't care about the mass number, which is why these two are correct. Does that make sense? Which of the following nuclides have the same number of neutrons? Okay, so for this question, you're going to need to know the formula. Neutrons equals atomic number minus I think it's mass number. Hold on, let me check. Again, sorry for the mic quality. Sorry, I got them mixed up. So it's gonna be neutrons equals mass number minus atomic number, so A minus Z. And what we're gonna do is, so applying this formula on all of them, all you do is 23 minus 11. So you get 12 number of neutrons. 24 minus 12, you get 12 number of neutrons. 23 minus 10, you get 13 neutrons. 25 minus 13, you get hold on. Is that 25? Okay, anyways, 25 minus 13. Hold on. You get 12, I think, as well. And then 12 minus 6, you get 6. So that means these three options have the same number of neutrons, so these three are correct. Which of these samples can be used as a radioactive source in Rutherford's experiment? Okay, so all you need to do is memorize the two sources, and that's all you need to know, like, on this radioactive source. So you need to know radium-226 undergoes alpha decay, and radon-222 undergoes alpha decay. Which of these will be enough to protect against a influx of beta particles? Okay, so the three ones you need to know is 20 meters of air, 10 centimeters of aluminum, and 1 centimeter of lead. One sheet of paper cannot protect you from beta particles, but it can protect you from alpha particles. So keep that in mind. Which of these will be enough to protect against a flux of alpha particles? So, as I mentioned just now, one sheet of paper is going to be enough. And, okay, so basically also 1 millimeter of aluminum and 1 centimeter of cardboard, like, of course it's thicker than a sheet of paper, and 10 centimeters of lead. So these all can protect from alpha particles. Which of the following correctly describe properties of protons emitted during radioactive decay? Select all that apply. Okay, so photons are odd sources of electromagnetic radiations as waves or as particles, and they're weightless. Okay, so they pass in a straight line through uniform matter. Yes, because that's why you can take an X-ray and see your bones. They are positively charged. No, they're neutrally charged. They're referred to as gamma radiation. Yes. Their speed is about 6% of light. No. And their ionizing ability is about 10 ion pairs per centimeter of air. Yes. Na is a symbol of the chemical element sodium. Drag and drop the representation of the sodium nucleotide that has 11 protons, 12 neutrons, and 11 electrons. Okay, so it's 23 and 11 because we know that there's 11 protons, so that immediately goes to the bottom. And then there's 12 neutrons and 11 electrons, so you just add those two. The atomic number of this nucleide is... Okay, this question's super easy. This is just 26 and this one's just 54. Complete the following diagram to describe penetrating power of different types of radioactive radiation. Drag and drop the correct answers. Okay, so we know out of all these three, the gamma ray is the strongest one. So obviously it can't be passed through lead, which, well, it actually can. So it can't, like, it's very difficult for it to pass, like, for it not to pass through anything. The weakest one is alpha particle, which is blocked by a piece of paper. And then the beta particle, blocked by, not blocked, yeah. Determine whether each statement is describing the electron, the proton, or the neutron. The particle is negatively charged. This is electron, you should know this. The particle is positively charged. It's proton. Neutron. The particle moves around in the nucleus. It's the electron. Match each statement with the type of radioactive decay it describes. Okay, so the helium is a nucleus, it's alpha. It's an electron, it's beta. The least ionizing effect is gamma, and it's a photon. For gamma. The unstable nuclide emits radiation in an attempt to become more stable. This is known as radioactive decay. Fusion occurs when we said this before, two light nuclei fuse together to form a heavy nucleus. Guys, most of this is just like memorization. In the Thomson's model, the atom is conceived as a collection of tiny blank and in a blank charged uniform medium resembling raisins in a pudding. Okay, so tiny electrons in a positive charged uniform medium. The number of nucleons in the nucleus of the silicon atom is... Okay, so the nucleons should be the mass number, which is 28 as given. The value of X is... Okay, so at the bottom we have 7 equals 6 plus 1. And at the top we have 12 equals 0. X plus 0. I'm just going to write it over here. So X is going to be 12. Consider the 3 isotopes of hydrogen. Drag and drop the correct isotope of hydrogen to its corresponding nuclear composition. Choose the correct answers to compare masses of different isotopes to hydrogen. Okay, so if they want 1 proton and 1 neutron, it's going to be 2-1. 1 proton and 2 neutrons is 3-1. And 1 proton and 0 neutrons is 1-1. Choose the correct answers to compare the masses of different isotopes to hydrogen. Okay, so H13 is obviously the greatest, and this one, and H12 is also greater than H11. Complete the following diagram to describe Chadwick's experiment setup. Drag and drop the correct answers from the box. Okay, so this is the extent of what you need to know for Chadwick's experiment. So you need to know that the source is alpha particles, and then it went through beryllium, it became neutrons, went through paraffin, it became protons. An atom of iron 2656 is neutral. This particular nuclear species, having values of Z and N, is called a nuclide. I don't know how to spell it. Okay, so there are going to be 26 neutrons because it's at the bottom. Then there are going to be 30 neutrons because you do 56 minus 26. And there are also going to be 26 electrons because 56 minus 30. An alpha particle is released by a nucleus of an unstable atom. What happens to the nucleus atomic number? Choose the correct answer. Okay, so let's imagine you have a nucleus of a particle. Let's call it X. And let's pick some random numbers, for example, 8 and 4. So now let's say you have a nucleus of another unstable atom, and let's call it Y. But we don't know the atomic number or the mass number. So let's add that by the alpha particle. So plus helium. And we know helium is 4-2. So we need to find what's in the box. So all we do is 4 minus 2, and you get 2. And you do 8 minus 4 and you get 4. So that's what happens. Okay, so we just saw the atomic number decrease by 2 and the mass number decreased by 4. The reaction shown is an example of I feel like we did this before. I think we did part C before for sure. So I'm just going to write 12. The reaction shown is an example of... Okay, so This reaction is an example of beta plus decay, and the particle labeled Y is a positron because the mass number is like 0 and the atomic number, the atomic number is 0 and the mass number is 1, I think. Yeah. So that's why it's a positron. The value of Y is blank and the value of Z is blank. The reaction is an example of blank and particle X is a blank. Okay, so we're going to do the same thing as what we did before. So 2 plus 3 equals Z plus 1. So you basically get Z as you get Z as 4, and you get, sorry, you don't get Z as 4, you get Z as 2, and you get 1 plus 1 equals Y plus 0, so you get Y as 4. Sorry, I got them mixed up for a second. So let's just write that down. These 2 and Y is 4. So yeah, the value of Y is 4 and the value of Z is 2. Sorry if I got it wrong. Okay, the reaction is an example of fusion, and particle X is an alpha particle because it's helium, so that's why it's an alpha particle. Radioactive material should always be securely stored when not used. The material that is best for lining the box in which radioactive materials are stored is lead, and the 10 centimeter walls of this metal will completely stop alpha, beta, and gamma radiation to 10% of its initial value. If its speed is 0.06 and produces 10 to the power 5 ion pairs traveled in the air, then this particle is an alpha particle, and 10 to the power 3 is beta, and 10 is just gamma. Guys, I'm sorry, I knew I mixed them up. This is 2 and this is 4. Sorry.